Hello, myself Nishan Kaushal, and today we'll be solving first internal paper. So let us begin. So let us solve question number first of our first internal exam. So the question is, write an algorithm to accomplish the task for polynomial px given in the following table using brute force technique. So as we know, as we know, we can represent polynomial as, let's say it's a variable. So we can represent the polynomial in the form of a of I into x to the power I. These are the values that are stored in array and multiplied by the x in a for loop, and they are added continuously in variable sum. So the algorithm will be initialize a variable sum to 0 for I equals for, for I to n, compute ai x to the value raised to the power I, and add it to the variable sum and return sum as an answer. So this is the code. So if we want to find how much iterations it would take, so as we know, for loop will run one times in first case, in second times it will run two times, in third case it will run three times, and up to n times. If we want to get the sum of these sums, it will be n into n plus 1 upon 2. So its answer will be n into n plus 1 upon 2. Okay. Now let us solve this by recursion method. In recursion method, we will continuously call the function until and unless its degree is equals to the 0, x degree is equals to 0 or less than the variable. So define a function named any name that a polynomial coefficient is. If a degree of a polynomial is 0, we will return that coefficient. Else we will recursively call the polynomial for degree x minus 1 and we will add coefficient of degree. So as it is a for loop, as it is an recursion function, so number of iterations it will be taking will be n, because it will be running n times, as there will be n values in an array, so it will take n iterations. Let us take the second case, dividing the polynomial by x minus r. So in this we will first arrange the polynomial in descending orders, then we will divide it by highest degree. Okay. Then we will write the division as a first term of an coefficient, multiply the x minus r term by the coefficient obtained in a step 3, subtract the product, and which will result in a new polynomial, and we will again do these steps until and unless it is less than the degree of x minus r. So let's take an example, x square minus 3x plus 2 divided by x minus 1. So as we know, x minus 3x plus 2 can be written as x minus 1 into x minus 2. So in this case we will call for loop, and as we can see, if this is divided by x minus 1, so its iteration will be n minus 1, right? And so it will run from 1 to up to n minus 1 terms. So if we do the sum of these terms, it will be n minus 1 into n divided by 2. And for recursion case, it will be same as n just like we did in brute force method. Just in this case, we will use recursion and call the functions continuously, else both the algorithms are same. In this case, we must know that the degree of polynomial should not be less than x minus r, and if it is the case, then we should return p of x. Let's go to the last case, that is dpx differential of polynomial. So in differential of polynomial, as we know, in this case all the polynomial will be divided continuously, right, in a for loop of 1 to n. So it will be same, taking one iteration, then two iterations at a time, three iterations at a time, up to n. So its number of iteration in this will be n into n plus 1 upon 2. Okay, and in brute force method it will be same as n, because it will do the recursion like this only. So in this case it will be n into n plus 1 upon 2, and it will be n. There is one correction, it will be n minus 1. So now we will proceed to question number 2. Let us start with question number 2. In question number 2, we are given some data, and we have to perform operations on these data. So before solving this question, we must know some basic concepts of floating point integers, like if a number is given as 0.5555 e4 or any number, it can be written as 0.5555 into 10 to the power 4. These two things means the same. So if we want to move this decimal, let's say after this 5, so it could be written as 55.55 e2. And if we want to move this point after here, so we could write it as 0.5555 e5. Okay, these are the basic things we should know. Now let us proceed with the question. In this question, first we have to perform subtraction with these two data. As we can see, after exponential, the number is same, that is minus 99. So we can apply subtraction directly on these 4 digits, and we can find the value of n1 minus n2. Same with this data as well, as number after e is same, so we can perform operation directly in both these two numbers. So if we see 0.5452 minus 0.5424, it will be 4, 12, 8, 2. So it will be this number, n1 minus n2 will be 0.0028, and these exponential numbers will be same, because if we do 5 into 10 to the power 2 minus 2 into 10 to the power 2, it will be 3 to the power 3 into 10 to the power 2. You can cross check it by doing 500 minus 200, which will be 300. It will be what? 300 only. See, this is the same thing. So when we find n1 minus n2, here we have to also find a message. In this, message will be underflow. The reason being underflow is that, as you can see, e raised to the power minus 99. That means that this number is 0.0028 into 10 to the power minus 99, which is very small number, and computers can't store this much smaller number. So this the message in this question will be underflow, right? Similarly, we apply this operations on this data. So 0.5452 E3 minus 0.5424 E3 will be same 0.0028 E3. Now we will do multiplication. In multiplication, we have to focus on some basic things like the number before exponential will be multiplied normally, like we do 5 into 2, it will be the same. Okay, but terms after e will get added, just we do normally in exponentials. So for data of multiplication, the operations will be 0.111 e151 into 0.4444 e to the power 50. So 151 plus 50 will be what? 201. So 201 is written directly, and if we multiply 0.111 with 0.444, this data will be 0.0493. Okay, so this number could be written as 0.0493 e 201. Now we could write this data also as 0.4930 e 200. Why we could write this data? Just visualize it as we have multiplied it with 10 and divided it by 10. So when we multiply any exponential number with 10, power get added, and when it is divisible by 10, power gets subtracted, right? So in this case we have subtracted, so exponential will become 200. Now the message will be overflow, because this data is very much big. Like, you could imagine it will be 0.493 into 10 to the power 200, which is a very big number, and our computer can't store this big information in single register. So the message will be overflow. Now we will apply this operations in second part as well. So 0.111 e to the power 10 into 0.1234 will be 0.13700974. I have find out these digits using calculator, so you can also use calculator. And exponential terms will be 10 plus 15, which will be 25, right? See, now in now we will write only 3 digits, sorry, 4 digits, because we have to follow the Mantissa rule, right? Here the max significant digits are 4, so we have to write 4 significant digits. So we will write it as 0.0137 E25. Now we could shift the decimal point to here and it will become 0.137 E24, e to the power 24. Now here the message will be loss of the digits 0974, right? Because of Mantissa rule we can't put this number 0.974 here. Suppose if someone moved his decimal points after 7, so this digits will be lost, because the performer or the user will assume that after 7 there will be infinite numbers of zeros, right? So this 0974 number will get lost. Now we will do division. In division, we will also use the same exponential rules, that if two numbers are divided, the power will get subtracted and numbers will be divided normally. So in first question, n1 is given as 0.9998 e1 and n2 is given 0.100 e to the power minus 99, right? So if we do n1 divided by n2, that will be 9.9998, and 1 minus 99 will be what? 100, right? So it will become 9.998 e to the power 100, or we could also write it as 0.9998 e to the power 101. And if we think about a message, it would be overflow, because this data is also very big to get stored in the CPU or a register, right? Let us see the second part. In second part, the number are given as 0.998 e to the power minus 5 and 0.1000 e to the power 98. When we divide these two numbers, the answer would be the same, 9.998, as the number is same. And exponential terms will be 90 minus 5 minus 98, and it would be minus 103. So it could also be written as 0.998 e to the power minus 102. Here message will be underflow, because e to the power minus 101 is a very small number, as I have explained it before. So here the message will be underflow. So this was the second question of our first internal test. Now we will proceed to our third question. Let us proceed with question number 3. In question number 3, we have to find associativity, distributivity, and digits with 4 mantissa, and data is given here, right? Let me just increase the size of my pen. So for associativity, we will use the law a plus b minus c will be equals to a minus c plus b. And if these digits want to be distributive, it should follow the rule a into b minus c, which will be equals to ab minus ac, right? And if this both is true, then we have to check for truncated, and if this both are false, we doesn't have to check truncated, right? So let us proceed with this question. We are given a equals to 0.5665 e1, b equals to 0.5556 e raised to the power minus 1 and c equals to 0.5644 even, right? So I have tell you concepts of addition and subtraction in previous questions, so I will not explain you this here. uh, so a plus b will be what? A plus b, as e is here minus 1, we will convert it to e raised to the power 1, so then number will become 0.0055. 5 6 will get lost because we have to find with up to 4 multiplier digits only. So here a plus b will be what? 0.5720 e raised to power even. Now we will subtract the c from a plus b, and what is c? 0.5644. So 0.5644 gets subtracted from 0.5720. This will be what? 0.0076 e raised to power 1, right? Now for my convenience I have converted it to e raised to the power minus 1 because RHS could also be minus 1, and to save our time I have converted it here only. It will be of use or not, we will see it ahead. Now a minus, now we have to do what? A minus c. So a minus c will be 0.21 e raised to the power minus 1, right? And now we will add b to a minus c, so b will be 0.7656 e raised to the power minus 1. Here we have converted a minus c to e raised to the power minus 1 because b is already in e raised to the power minus 1 state. So we will convert it to the e raised to the power minus 1 state, and then we will add it to the b. So you, if we see this digit and this digit, we can clearly see that LHS is not equal to RHS, right? And if LHS is not equal to RHS, it doesn't satisfy associative property. And if it doesn't satisfy associative property, it will not satisfy distributive property. But we can check it here as well. A into b minus c, we will find that will be what? 0.2494 even. This calculation you can do it on your own, and AB will be this and AC will be this, and AB minus AB will be 0.2495 e raised to the power even. Okay, so it is not distributive as well, so it is not associative, not distributive, so we doesn't have to find truncated as well. So this was our question number 3. Now we will proceed to the next section, that is true or false. Let us proceed to our next segment, that is true or false. So our first question is minimize the number of arithmetic operations whenever possible. Uh, so this should be true because when we minimize our arithmetic operations, what we do is it increase efficiency of our program. Second, we also increase accuracy, and we also decrease our system memory usage. As we know, each and every operation needs a memory, so we can store that operations. If we decrease these operations, the memory usage will be less, and that will help our system. So this answer should be true. Let's see second question of our true and false. Second question is avoid taking the difference of two nearly equal numbers whenever possible by alternate formulation of the problem. If it cannot be avoided, take the difference before doing the operation. So this should be true Let us take an example to explain this. Let's say A is 1.00006 and B be 1.000000005. So when we perform operation like C equals to A minus B, its answer will be what? 0.000. How many zeros are there? 1, 2, 3, 4, 5, 6, 7. 0, 0, 0, 0, 0, 0, 0, 1. It could also be considered as 1, also be considered as 0, sorry. So if we further use C in any other operation and we by chance take the value 0, this will compute an error. So this answer should be true, that we should avoid taking the differences before doing any other operation. Got it? Let us proceed with our question 3 of our true and false. So the question is, adding or subtracting numbers start with the smallest number and works with the numbers in ascending order. This should be true because let us take an example. A equals to 45.53, B equals to 0.0000005, and C equals to 2.003. Right? So if we start adding number in a order of biggest to smallest, then we should perform this like A plus C plus B, right? But in this case, user can neglect this number and it could cause an error in our answer. But if we start adding number like B plus C plus A, then this B cannot be neglected. It increases our accuracy of our answer. So this should be true. Let us proceed to our fourth question. Do not formulate an algorithm that tests whether a floating number equals to 0. See, this should be true because in floating point numbers, like this is a number 0.005 e raised to the power 5, right? If we shift this point to here, then this could become 0.000 e to the power 6, right? And this could cause an error in our program, right? So this could cause error in our program. So we should not formulate an algorithm that tests a floating point number. So it should be true. Let us proceed to our fifth question. Ill conditioning of a problems is normally due to improper formulation and can be eliminated by carefully reformulating the problem. A practical way, if we detect the suspected ill conditioning, is to alter the parameters by a small amount and observe their effect on the solution. Yes, this should be true because let us take an example like we have a number A equals to 1.00005 and B equals to 6, right? So if we do a plus b and consider this number as approximately to be 1, then answer would be 6, right? this answer would be this answer we will get very fast, but its accuracy is very low, right? Because if we consider this as 1.00005, then answer would be something else. Answer would be 6.00030, right? This would be the answer. See, we could see the difference of 0.000030, right? And this could cause error in our program. In long, in this sort operations, this effect will not affect our program, but in long operations, it could affect our program very much. So, ill conditioning should be suspected. So, this should be true. Let us proceed to our sixth question. After numerical algorithm is obtained, check if it can lead to numerical instability. In such algorithms, error grow in each step of the calculation. In such cases, reformulate the solution procedure to get a stable numerical algorithm. This should be true because let us suppose take an example. A equals to 0.566542, right? And B equals to 0.55555, right? If we do A multiplication B in some operation, right, its answer can be restricted to few digits only, and some digits will be neglected, and this could cause error in our program, right? So to solve one way to do is use different data types like double float, which will just double our mantissa size so that there could not be any error in our program. But yeah, uh, but considering this question, this should be true that after numerical algorithm is obtained, we should check that it is not leading to any numerical instability. Let us see question number 7. If a severe rounding error and consequent loss of significant digits are anticipated and no alternative formulation to avoid this is possible, then carry more significant digits in the critical calculations using floating point numbers in double precision mode. In this mode, the length of the mantissa is twice that than the floating point quantities. Yeah, this is true. We have discussed it in question number 6, that if a program is giving an error by doing some rounding of errors, so it could be avoided using double floating point quantities, right? So this is, let us proceed to question number 8. Question number 8 is double precision requires large memory space and slowdowns calculation. Yep, this is true because in double precisions the number of bits will increase, and if number of bits increases, the memory space will be required more, and if number of bits are more, then the calculation will become complex and it will slow down our calculations. So this is true. So our question number 8 is double precision requires large memory space and slow down our calculation. Yes, this is true because in double precision the number of bits increases, and if number of bits increases, memory space also, memory space required also increases, right? So this is true, and it slow down our calculation. Yep. If our bit increases, the complexity of our calculation also increases, right? And if complexity increases, it will take more time to get solved. So it slows down our calculation as well. So this answer is true. So let us proceed to our question number 9. In the third iteration of finding the square root of 5, the starting point is 7. Using the Newton-Raphson method, relative error is 0.0013. So in Newton-Raphson method, the general formula is xn plus 1 equals to 0.5 xn plus 0.5 upon xn. So as we have given x0 is 0.7, so we will find x1 x1 so x1 will be 0.5 plus into 7 plus 0.5 upon 7, that will be 3.0714. Similarly we will find x2 and x3. Now relative error formula is xn plus 1 minus xn upon xn plus 1. So in third iteration, see, this is first iteration, second iteration, third iteration. Third iteration n will be 2, right, for relative error. So the relative error formula will be x3 minus x2 upon x3. So we have calculated relative error, that is 0.0013, and what we want is 0.0013. As both are same, so answer is 2. The iterative method are compared on the following parameters: the rate of convergence, the amount of computational effort per iteration, and the sensitivity of a method to the starting value and the intermediate value. This is our question number 10, and this is true because these are all the facts that the iterative methods have the following parameters like convergence, computational effort per iteration, and sensitivity of the method, right? So this is true. So with this, our first internal paper is solved. Now we will solve second internal paper. Thank you.